Hello. Today, I would like to talk about the ESP32 chips and some of their pitfalls with timekeeping. Their clocks are often good enough, but for some projects you have to be aware that they can drift by minutes in just a couple of hours. I'm going to focus on the ESP32-S3, but everything is valid for most ESP32 chips. You can completely stop the clock from drifting if you prevent the chip from sleeping. But that is not a good option when your project is powered by a battery. So I wondered, first, what causes the behavior, and second, what can you do to fix it? The ESP32 chips derive their clock from 4 sources. The main clock is an external 40 MHz crystal, which is accurate up to 10 parts per million. Then there are 2 internal RC oscillators that aren't specified for tolerance or stability. And finally, there's an external 32 kHz crystal. This crystal, however, is optional and usually not included in modules or development boards. Whenever the ESP is active, time is kept with a 40 MHz crystal. It will then drift by less than a second per day. During sleep, however, the crystal is powered down and time is kept with a slow RC oscillator. I'll refer to this oscillator as RTC. Therefore, the issues with clock drift must come from the RTC during sleep. You can configure the firmware to use the fast RC oscillator instead, or the 32 kHz crystal. This could improve accuracy but costs additional power. I'll go through these options later. Now let's test the RTC clock. First, I'm going to synchronize the clock over Wi-Fi. After that, I'll fetch the current time every 10 minutes and compare it with the RTC clock. I ran this loop for 14 hours. This is the result. On the x-axis is the actual time, and on the y-axis is the time on the chip. You can see that it's linear, but nothing else. Let's make a better picture. Clock drift is when the clock gradually becomes more and more inaccurate, and the offset is the difference between the chip's clock and the actual time. Now I put the offset in seconds on the y-axis. In the 14 hours of runtime, the clock drifted by slightly more than a minute. There's also an overall downward slope to the offset. This slope means that the firmware believes that the frequency of the RTC is higher than it actually is. How does the firmware come to a belief about the frequency? It figures out the frequency of the RTC by running a clock calibration routine during boot and whenever it wakes up from sleep. This routine measures 1024 cycles of the RTC against the accurate 40 MHz crystal, which takes around 7 milliseconds. You can configure the number of cycles it uses. And if you read the documentation, it says to increase the number if precision of time during sleep is important. However, we will see later that this won't do much about the clock drift. It just takes more time and power. You can also disable the calibration routine by setting the number of cycles to 0. This will save those 7 milliseconds, but you should then calibrate the frequency yourself. The clock calibration routine, however, is quite easy to improve upon. Just recalculate the RTC frequency whenever you synchronize the clock with NTP. The frequency is simply the difference in RTC cycles divided by the difference in time. Or in other words, the period is the difference in time divided by the difference in RTC cycles. You then need to store the period in an internal register in the correct fixed point format. For the experiment, I split the data in 2. I used the first 7 hours to calculate the oscillator's period and the next 7 hours to evaluate the drift. This makes the graph of the offset better. First note that the offset returns to 0 after 7 hours. This is because those 7 hours were used to calibrate the frequency. The offset after the following 7 hours is reduced to 21 seconds, which is a free improvement by 36%. Wow! I'd like to investigate why the clock drift didn't vanish though. But first I need to look into these spikes. Here, the offset suddenly changes by a couple of seconds, and it could be either irregularities of the oscillator or outliers of the measurement. Let's talk about how the clock synchronization works. On the top is the timeline of the server, and on the bottom the timeline of the ESP. At some point in time, the chip sends a request for the current time to the server. After processing it, the server sends a response back to the chip. This procedure can be simplified to these 4 points in time: when the request was sent and received, and when the response was sent and received. The 2 clocks are then synchronized by equating the midpoints of these intervals. This works because the midpoints should be aligned, that is, they should refer to the same point in time. However, if the end-to-end delays are not symmetric, then the midpoints do not align and the clock synchronization becomes inaccurate. The uncertainty of the synchronization can be quantified by the total time required for sending the request and sending the response, which is called the round-trip delay. On the graph of the clock offset, I now overlay the round-trip delay. You can see a couple of things. First, the median round-trip delay was quite short at below 50 milliseconds. However, some requests took substantially longer. 3 requests even took over 3 seconds to complete. I marked all outliers with vertical lines, and they match the spikes of the clock offset perfectly. Therefore, I remove the outliers. This fixes the data, and the graph becomes fairly smooth. Let's get back to why the clock drift is still there. Next to regularly fetching the time from a server, I also recorded the temperature with the on-chip sensor. The temperature looks jaggy because of the sensor's resolution. Furthermore, it shoots up by up to a degree every 10 minutes, and this happens whenever Wi-Fi is turned on. Overall, the temperature was rather stable and mostly between 23 and 25 degrees Celsius. When I overlay the clock offset from before, a simple pattern emerges. Whenever the temperature is constant, the clock offset changes more or less linearly. You can see that here, here, and here. So different temperatures result in different slopes. And since the slope is related to the period, I'm going to plot the period instead of the offset. This reveals a good agreement between the fluctuations of the temperature and the RTC period. Now, as a final refinement, I will filter the temperature. For every interval between 2 successive requests to the server, I calculate and will now graph the average temperature. An almost perfect match. Wow! This allows me to determine the temperature coefficient of the RTC. First, let's graph the temperature against the period directly. This looks fairly linear, and a linear regression immediately gives the temperature coefficient. The clock drift turns out to be around 2 minutes per day for every 1 degree of change in temperature. I wanted to increase the reliability of this estimate, so I repeated the measurement for a total of 2 weeks. Again, you can see that the temperature and the period match over time. This time the temperature had a slightly larger range from around 21 to 26 degrees. When graphing temperature against period directly again, the relation is linear with a temperature coefficient of again around 2 minutes per day for every 1 degree of change in temperature. Lastly, I want to check out how well you can compensate this enormous clock drift. The observation was that the period of the RTC behaves roughly linear in temperature. This can be expressed as a regression equation, which I can then use for the compensation. Here are the 2 measurements. On the left, there are 14 hours of data using the first 7 hours for the improved calibration routine, and I got an offset of 21 seconds. On the right, I collected 2 weeks of data and used the first 2 days for the improved calibration. This had an offset of around 25 minutes. After temperature compensation, the offset on the left reduces to 3.6 seconds, a 6-fold improvement. And on the right, the offset reduces to 52 seconds, which is a 30-fold improvement. Wow! In conclusion, the default RTC of the ESP32-S3 drifts by around 2 minutes per day for every 1 degree of change in temperature. The fast RTC, which I measured separately over the course of 2 weeks, drifts by around half a minute per day for every 1 degree of change in temperature, but it requires an additional 5 microamps of current. If the temperature sensor is regularly sampled during sleep, it's possible to compensate the RTC for lower drift. However, an external crystal will always have significantly lower drift. Stability is usually better than 200 parts per million over the whole temperature range, which is around 17 seconds of total drift per day across all temperatures. And it requires just an additional 1 microamp of current. So, use the default RTC if its drift is acceptable for the application. And if you require lower drift, use an external crystal. Thank you for watching.